Just a few weeks ago, NASA took the first steps towards planetary defense. They did this by crashing their satellite, DART, into the asteroid Dimorphos. But the question on all of our minds right now is, did it work? I'm Josiah, and I'm a space engineer, and we're going to get a little bit into the math of whether this worked or not, and of course, what this means for planetary defense in general. And of course, we're going to answer the big question. Could we really deflect an asteroid if it was coming right towards us? So just to be clear, the asteroid Dimorphos is not actually on a collision trajectory with the Earth. So this is just a test. NASA was trying to see if their new method of crashing something into an asteroid would actually be enough to deflect it. And they picked this particular asteroid for some very specific reasons. Dimorphos isn't actually an asteroid all by itself. It's actually in orbit around another asteroid, which is a little bit bigger, called Dimorphos. Because of this unique configuration, you can actually see the changes in Dimorphos' orbit around Dimorphos relatively quickly. It only orbits every 12 hours or so you can figure out relatively quickly if there has actually been a change or not. So the main way that we can figure out whether this was successful or not is to actually look at the data that they collected afterwards to see how much the orbit of Dimorphos actually changed. And then we can actually use that information to tell us how much energy was actually transferred from DART into the asteroid, and we can kind of extrapolate those numbers to some other asteroids that might actually be coming towards Earth in different types of heliocentric orbits. So there'll be a little bit of math along the way, but trust me, it'll be a little bit interesting, and the answer we come to in the end may actually surprise you. So here you can see the data that was released by NASA, and here are the important bits. So up here in the top graph here, with the gray arrows, we have the location of Dimorphos if it hadn't been impacted. So basically, if things had just carried on as normal, we would expect it to do one orbit every single time we see one of these gray arrows, about every 12 hours or so. And then with the orange arrows, we see the actual appearance of Dimorphos as it was seen by the telescopes. And basically what this is looking for is a dip in the light curve for when Dimorphos goes in front of Didymos, because that means that it gets a little bit less bright when that happens. And that's where you see these little dips that are occurring, and that's where they assume that the transit of Dimorphos is happening. Here you can see on the bottom there's a little bit more of a zoomed in version of this for September 29th and for October 4th. Of course, they can't have continuous data observing this asteroid because, well, Earth is turning, so for half the time you're not even going to be looking at it. And of course, there are other things that get in the way, like clouds and weather. So this is why you don't get a complete graph of what's going on. But they have enough data here that they can basically be pretty sure that this is the way that it's going. The basic summary is that instead of it being an 11-hour and 55-minute orbit, as it had before, it now has an 11-hour and 23-minute orbit. And if we consider that NASA's definition of success was to have an orbital change of just a minute and a half or so, this is definitely a resounding success. So congratulations to the DART team! You've successfully redirected an asteroid! So yes, NASA was able to deflect the asteroid, but what does this actually mean for deflecting an asteroid that's headed towards Earth? Of course, Dimorphos is not actually headed towards Earth, it's just orbiting another asteroid, which means that the situation is a little bit different. If we do some orbital mechanics, we can actually figure out exactly how much delta V was actually taken away from Dimorphos in this collision. And this is going to help us to figure out whether this would actually be effective for deflecting an asteroid that would be headed towards Earth. It turns out that the orbital speed of Dimorphos is actually only 0.174 meters per second, which is pretty slow. Like, you could totally walk and be faster than Dimorphos is when it goes around in its orbit. It only travels a distance of about 4 kilometers in half a day. Of course, it's Dimorphos' size that's actually what makes it hard to move. It's about the size of the Pyramid of Giza. Nonetheless, even with this orbital change of around 30 minutes, it actually corresponds to a delta V change of about 0.003 meters per second, which is really, really tiny. But here's the big question. Would this actually protect us from an asteroid that was actually hurtling towards Earth? Well, using the power of math, we can figure that out too. Let's imagine a slightly different situation where we actually have an asteroid that's coming on a trajectory towards Earth. The question is, would this delta V that we got out of the Dimorphos collision be enough to deflect an asteroid that was on that type of a trajectory? To do this, we basically have to use the Wies-Viva equation and Kepler's orbital equation in order to determine what the period of the orbit for the regular asteroid that's going to hit Earth and the period of the asteroid that gets impacted and will hopefully miss the Earth. After some quick calculations, we discover that that difference in period is actually around 11 seconds. 11 seconds, that's it. For the entire year of this asteroid's orbit, we're changing it by just 11 seconds. So is this enough to actually cause the asteroid to miss Earth? We know that Earth's diameter is roughly equal to 12,800 kilometers. And we know that Earth's speed around the sun is roughly equal to 30 kilometers per second. So this means that if we take this 12,800 kilometers and we divide it by 30 kilometers per second, we can figure out how long it actually takes for Earth to move its entire distance of itself in its orbit. So if we actually do this calculation where we take 12,800 and we divide it by 30, we get to an answer of around 426 seconds. So this means that in order for us to actually have an asteroid miss the Earth, we need to deflect it by more than 426 seconds. And we know here that we're only able to get about 11 seconds. So if we wanted to make sure that we did this soon enough, we'd have to actually hit this asteroid by 426 divided by 11 years ahead of schedule. So we have to make sure that we hit it 38 orbits ahead of impact. So from this, basically what we can tell is that we're roughly 2 orders of magnitude away from the energy that we need to protect the Earth from an asteroid that would be roughly the size of Dimorphos. And of course, there's basically like 2 ways that we can go about trying to compensate for this. So the first one would be to, of course, try to predict Dimorphos' impact far, far in advance. In this case, we need about 38 orbits in advance. So that means that we need to be roughly 50 years prior notice before we would be able to properly deflect an orbit of an asteroid like Dimorphos like this. That seems a bit unrealistic because these asteroids like Dimorphos are really small and hard to detect, and figuring out their orbits 50 years in advance is like a bit of a challenge. What's a bit more likely is maybe we could try to scale up the DART mission. So in this case, DART was only about 610 kilograms. But of course, we can launch bigger things into orbit and into orbits where we could actually deflect an asteroid. Like if we look at today's rockets, we can easily see a situation where we could launch something on the order of 6,000 kilograms. That's for sure a possibility. You could launch something like this on a Delta IV Heavy or a Falcon 9 Heavy, or even on some future missions like SLS or Starship. If you step up to maybe some future rockets that we might be having available, ones that can launch something on the order of like 60,000 kilograms into an orbit that could go and deflect an asteroid like Dimorphos, you're really stepping into the energies where we could actually realistically deflect an orbit of an asteroid like that in a realistic time frame of just a couple of years. Of course, there are some more complicated orbital dynamics that are happening. I kind of use some simplified formulas that are useful for small objects orbiting around a sun without anything interfering with their way. But of course, there's also other little interactions with like Mars or Earth or Jupiter, which can kind of cause things to get a little more complicated. And sometimes it'll change the answer that you're actually getting. But in this case, I would say that we're roughly in the ballpark of where you would expect this answer to be. But it's really positive because it means that we actually do have the power to deflect an asteroid if we get our impactor a little bit bigger and we have enough advance warning. So in the end, I would say this is really good news. The key to success is having the right rocket for the job. And in this case, the bigger the rocket is, the better. So let's keep supporting those rocket building companies because they could be the difference between Earth's life and death in the future. And remember to keep expanding your horizons.